Okay, so in here it's called the squeeze. It's sometimes called the squeeze theorem. That's my shorthand for theorem, th to the power of m, because I'm too lazy to write all the other letters. It's also called the sandwich theorem or the two cops theorem. And I'm going to say it in words, and then I'm going to draw a picture, and it'll make perfect sense. Okay? So basically, if you have a limit that you cannot figure out, all right, because you can't remove the discontinuity, but you know two limits that bracket it and squeeze that limit between it, you just have to find those two limits, and then you know this limit. Perfect, right? Makes sense? This is what it means visually. That's what this says. Suppose f, b, and s are functions such that s of x is less than f of, or s of x is less than f of x is less than b of x or equal to, around some interval containing a constant c. If both the limit of x goes to c of s of x is equal to L and the limit of x goes to c of b of x is equal to L, then the limit as x goes to c of f of x has to equal L. What the heck does that mean? It means this. Here's c. I'm just going to draw some functions. Here's s of x. Let's do b of x. Oh, helps if you draw it right. There's b of x. And we know that f of x is between them. It's not the best drawing, but. So you can see, if we know that as we get close to c, s of x goes to a certain number, the limit would be L. There's our L. And b of x goes to the same number, right? And our function that we cannot figure out on its own is squeezed between them. As long as we know these two limits, then we know the limit of the one that goes between them. Does that make sense? That's all the squeeze theorem is saying. If you squeeze the function at a certain point between the two other functions, you don't need to find the limit of this function directly. You can find it indirectly by knowing those two limits. Yeah? So what does this look like? I'll give you an example. I don't know if she's going to ask you to do one. All the examples I've ever seen in Math 100 are trig examples because they're actually easier. So if I said, find the limit as x goes to 0 of cos 1 over x. Sorry, of x cos 1 over x. That one. Okay. Well, I can't sub in 0, can I? No. But this is why we like trig functions. For every single sine and cosine function, no matter what this is, 1 over x or x squared or whatever, what is cosine or sine always between? 1 and -1. That's all it ever does. Right? Here's the cosine graph. No, here's the cosine graph. You can't see that. Let me draw it on the board. Cosine graph, no matter what, just does this both ways. Right? That's all it does. The only way to change that is to add in an a value. Remember that? Transformations. Then you're doing a vertical expansion and a d value that shifts it up, a vertical translation. If you don't have those two, then it's always between 1 and -1. Okay? As x gets really, really big, it just keeps oscillating between 1 and -1. And as it gets really small. So we can write that mathematically like this. So I look at this and I go, okay, cos 1 over x is always going to be between 1 and negative 1. No matter what you do, no matter what number you put in there, you can put any number you want. You can do it on your calculator. The number you get will be between 1 and negative 1. Okay? Are we good with that? But that's not the function I want to figure out. I want to figure out x cos 1 over x. So if I multiply through by x, so I multiply this by x, and I get negative x. Multiply the middle one by x, I get this. And then the end is x. All right, I didn't violate any mathematical laws. That's like algebra, whenever you learn algebra. I don't know when you learn algebra. Grade 8, grade 7. What you do to one side, you have to do the other side. So we just multiply everything by x. Okay, is this still a true statement? Have I changed anything? Can you find the limit of x and negative x as x goes to 0? So I can go, if I could write, the limit as x goes to 0 of negative x. What does that equal? 0. The limit as x goes to 0 of x is equal to 0. Therefore, the lim as x goes to 0 of x cos 1 over x has to equal 0. Is that okay? I'll show you what it looks like visually. Let's wait until everybody writes that down. So if we do it, here's the graph of cos 1 over x. So that's the graph I'm trying to figure out. Now, if you just look at the graph, you can see it's going to go to 0. But if I put in negative x, and then I put in x, you can see it gets squeezed between those two lines. So even though this function here is undefined at 0, like if I hover over it, see if I can get there. Not gonna be able to get there. Whatever. Anyway, it's undefined at 0, but if I squeeze it between the x and the negative x, it's a squeeze theorem. Now, the only other, it's sort of like epsilon delta in that the ones that I've seen in Math 100, they just give you trig functions because it's easy to border it with 1 and negative 1. When you start to use different functions, it gets much more complicated. All right, and we're in kindergarten calculus right now. So it's just the idea you have to understand. Does everybody understand the idea? If I can squeeze a function between two other functions, as long as I know those two other functions, I know the limit of the middle function. That's the basic idea. All right, we okay with that? Okay, we're going to use it to prove sine x over x, which is the next page. This thing. I don't think this will be, you'll be asked to reproduce this. I've never seen it asked or been asked to reproduce, but it's a good application of this. So we're going to pretend we're on the unit circle. So our radius is 1. And we're going to make 3 areas. So there is this little area, this triangle right here, which is drawn right here. Okay. What's the area of a triangle? The formula. Yeah, 1/2 base times height. So the area of a triangle is 1/2 base times height. Okay. If we look at this one, so the height is this. Oh. The base, since we're on the unit circle, this bit is this bit right here. So it's 1. And the hypotenuse here will be 1. Well, it's not technically the hypotenuse, but that'll be 1 too. Okay? Does everybody agree with that? Unit circle, this is the triangle we're doing. So base is 1. The height, this thing right here, we're going to write it as a function of theta. And we're going to use sine. Sine is what over what? What side over what side for sine? Trig. Yeah. So if that's the height, sine theta, I'm going to write it right here. Sine theta is going to be h over 1. So in other words, h is equal to sine theta. Does everybody see that? Because it's just a 1. So instead of writing h here, I can just write sine theta. So now the area of that triangle is sine theta over 2. Okay, we'll just leave that for a sec. Now the next one, what we do is now we're going to use the curve here. Come on. Okay, now we're going to use the curve here. So, what's the area of a circle? Formula for area of a circle? Pi r squared. So, area of a circle is going to be pi r squared. Now, this is a section of a circle, right? Like this, I could extend that. It's a full circle. That makes sense to everybody? Yeah.
For the first triangle, isn't the base a little less than 1 because the height is moved over?
Yeah, that's the height, but we're doing the full triangle. When you do the area of a triangle, it's still 1/2 base times height. Yeah. So yeah, you're right. Like it looks like I drew it to there, but it goes all the way to there. That's the base. So if I do half a circle, what's the formula for area of half a circle? It's divided by 2. If it was a quarter of a circle, it would be divided by 4. So what you're actually doing is the ratio of this angle. Okay? So the ratio of the angle is going to be whatever the angle is divided by 360, which I'm going to fix in a sec. Okay? So if it's half a circle, it's 180 over 360, which is 1/2. That's why it's pi r squared over 2. All right? We don't want 360. What's 360 in rads? 2 pi. And our radius, what's the radius of the unit circle? It's 1. So I can put 1 squared. If you simplify this, boom, boom, you're going to get theta over 2.
Why do they make blue
I don't know. Okay, is everybody good with that? So which one's bigger between the two we've done? Look at the picture, the original picture. The one with the arc length or the one with the first triangle? The arc length one, right? See, it's got this little extra bit there. So we can say that this one is less than that one. All right, the next one is when you extend out all the way out here, like that. Okay, that's what this next one is. So again, that's going to be a 1. That's going to be our height. So I'll just label on here height 1 theta. Area of the triangle is 1/2 base times height. What's your base? 1. Your height. What trig function is going to involve h and 1? Not sine. These two sides. Tan theta, right? Tan is opposite over adjacent. Remember our right angle trig? So that's going to be, our height is going to, so if I write that, go away. Tan theta is equal to h over 1. Therefore, h is equal to tan theta. Is everybody good with that? So I get tan theta for h. So we get tan theta over 2. Okay. Is that bigger or smaller than the other two? It's bigger. It's the biggest one. So we can say that. So now we've got our ratio. I'm going to rewrite it right below. So we have sine theta over 2 is less than theta over 2 is less than tan theta over 2. Okay. We're going to multiply through by two over sine theta. Everything gets multiplied by 2 over sine theta. What happens to the first term? This one goes to, and you left with 1. All right, so we get 1 is less than, what happens to the second term? The middle one. The 2's go away, so we get theta over sine theta. And the last one, we're gonna, 2's will cancel. We're gonna clean it up in a sec here. We got tan theta over sine theta. I don't want tan theta over sine theta. What's tan? Sine over cos. So if I'm over to the side here, tan is sine theta over cos theta, and it's all over sine theta. What does that become? 1 over cos theta. So now I've got this. We got that. All right. Is everybody with me? Okay. I'm going to flip them all because I'm trying to prove this. Sine theta over theta. Okay. We have theta over sine theta. So you can flip them all the fractions, but when you flip fractions, all the inequalities switch as well. If you think about it in numbers, if I have 1/2 is less than, no, 1/2 is bigger. Bigger than 1/3 is bigger than 1/4. Is that true? It is. If I flip all the fractions, 2, 3, and 4, what do I have to do to all the inequalities? You have to flip the inequalities, okay? So I'm going to flip all these. The 1 stays the same. So now I have this. Okay. We're trying to prove the limit of sine theta over theta as theta goes to 0. We've shown that sine theta over theta is bracketed by these two functions, 1 and cos theta. Can you find the limits of those two functions? You can. So we go, the limit as theta goes to 0 of 1 is equal to 1. The limit as theta goes to 0 of cos theta, what's cos of 0? 1. Therefore, the limit as theta goes to 0 of sine theta over theta has to equal 1. That's one of the proofs of that function. Okay? I don't think you're going to be asked to repeat it. But just to show you it doesn't come from nowhere. You can show it graphically. Graphically is a little more interesting. If we do sine x there's the graph of sine x over x. If I do y is equal to 1, there's that graph, and then cos x, you can see that it gets squeezed between them as you head to 0. So as long as you know the two other limits, you know the limit of that one. Okay? All right. Short of it is you need to know those two limits. I proved the other one yesterday. So as long as you know this limit, because you're not going to get it, as far as I know, it will not be given to you. So you should remember that one. And then the other one was limit as x goes to 0 of 1 minus cos x over x is equal to 0. Those are the two limits you need to remember. Okay? So every time you're doing a trig limit, your goal is to make it look like the one of those two limits. Now, there was a really good question she had on here. Where did it go? This one. So if you go to page 75, this one, example 18. I really like this question. Two x plus 9 minus cos x plus 4 over x plus 4. Okay. Does that look like anything that we've done? It's got a cosine in it. It's got the fact that what's inside the angle, x plus 4, matches the denominator. That's a good thing, because we showed yesterday if you do a substitution, you can clear that out. But you got this 2x plus 9. So does anybody have any ideas of what to do? How are you going to split it up? Okay. Don't write this down. No, that's the intuitive thing to do. But so if we do this, that's what you want to do, right? No, don't. Yes. Somebody had to do it. Say it, right? It looks like it's the right thing. Problem is, what's the cosine limit? The special one. It's 1 minus. If it was sine, if this was sine, that would be the right thing to do, because all you care about is sine over some number, right? But the cosine one has got this 1 in front of it. So you have to find a 1. Where are you going to find a 1? That's exactly what you want to do. So you want to take a 1 from the 9. Because in your head, you should be thinking, I want these to cancel, right? I want this x plus 4 and this one to go away. Correct? Because if it goes away, then I can just sub in. That's your whole goal, is to sub in, right? So if I can make that go away, but I can't factor a 2 out of here. Well, you can, but it's going to be a decimal. So it doesn't help you. But if I take 1 away from the 9, what do I get? 8. And then you can take a 2 out, and you generate a 1 that matches this. So you rewrite it like this. So I'm going to erase this. And I'm going to rewrite it as 2x plus 8 plus 1 minus cos x plus 4 over x plus 4. All I did is rewrite the 9 as 8 plus 1. That's all I did. That's legitimate, right? I can write the 9 as 1 plus 1 plus 1 plus 1 plus 1 plus, I can do it 9 times. But I only need 1. Now you want to split it. Because you've got the identity that you wanted right there. Well, that didn't work. Right there. That's how you want to split it. So we're going to go the lim as x goes to -4, 2x plus 8 over x plus 4 plus 1 minus cos x plus 4 over x plus 4. Does that make sense? Okay, we're not done yet, but we're on the right track. Okay. For the first part, 2x plus 8, what do I want to do? Factor 2 out. So I get the limit as x goes to -4, 2x plus 4 plus, I'm going to rewrite this as the lim as x goes to -4. Remember, you have to write limit every time. So on the first part, yeah. Why did I make it into 2 limits? Because technically, this is a special limit, so I'm going to have to rearrange this. And you remember the limit properties I did the other day? Yeah. If you're adding it, so you can break them into 2 separate limits. So this is technically what you should do, because this, I can't just plug 4 into this, or -4 into this. I'm going to have to rewrite this before I do that. Okay, so this is going to become a different limit. All right? But this one I can do because the x plus 4s are going to cancel. Boom, boom. So you're left with the lim as x goes to -4 of 2, which is 2, right? Because that's a horizontal line. So that part's 2. But now we got to deal with this thing over here. Why can I not say that is 0? Yeah, it's not, our definition is this, right? It's as x goes to 0. So you have to manipulate that to make it fit that. So we have to do a substitution. Now I know this seems kind of like, what's the point? We know it's going to be 0. But you have to do this because they're not the same thing. If you just write 0, you're going to lose marks. Guaranteed. Okay? So the substitution, what variable do you want to use? Okay, so a is equal to x plus 4. So then you ask yourself, okay, as x goes to -4, what does a go to? 0, because you're doing a mini limit when you do this part, right? X plus 4 is a linear function. Starts at 4, goes up 1 over 1. So it looks like that. That's what you're doing. So I'm saying, okay, I'm saying a is x plus 4. As x goes to -4, this goes to 0. A goes to 0. So that's what you're doing. So then you sub that back into here, and we get the limit as a goes to 0 of 1 minus cos of a over a. That matches our definition up here, this thing. I mean, the variables are different, but that doesn't matter. So now you can say that limit is 0. And when you plug in the number, the limit disappears. You don't write limit anymore. Okay? So that's why I'm not writing lim here. I'm not writing lim 2. Okay? Once you sub it in, the word limit goes away. So it's 2 plus 0, so the answer is 2. Okay? We end at 10:08. We're done. Finish that sheet. Make sure you can, and the assignment is up.